Today I'm going to be talking about atomic and ionic radii trends in the periodic table. So first of all, an atomic radius is basically how big the atom is. Electrons don't actually orbit around the nucleus in perfect circles, but instead surround the nucleus almost like a cloud, like shown here, and they move around in their own energy levels and orbitals. Because of this, atoms don't have a definite spherical shape with a definite radius. Instead, the atomic radius is actually measured by first finding the distance between two atoms of the same element covalently bonded, like so, and half of that distance would be the radius. So if, for example, these two atoms were hydrogen atoms, this would be the atomic radius of hydrogen. When we continue to look at examples like shown here, we can simplify the diagrams just to make everything a bit easier and more clear. We can just assume that this is the atomic radius. We can see here that lithium has a much greater atomic radius than hydrogen. Let's first look at trends within the groups, and we can take hydrogen, lithium, and sodium as examples. Here you can see as you go down the group of elements, each one adds another energy shell, so obviously this makes the radius much bigger. So you can see on the periodic table, atomic radii increase in this direction as we go down the rows. Next, let's look at trends within periods. We can take lithium and beryllium as examples. Here is lithium with 3 protons, and beryllium with 4. The more protons there are, the stronger the positive attraction of the nucleus, pulling the negatively charged electrons closer. So here, beryllium has more protons than lithium, so it has a stronger pull on the electrons, bringing them closer to the nucleus, making the atomic radius slightly smaller. So if we look back at the periodic table, we see that the atomic radius gets smaller in this direction, so it increases in this direction, like so. So atoms down here generally have larger atomic radii, and atoms up here have smaller atomic radii. However, as we go in this direction, the increase in atomic radii isn't that much, but when we go down the groups, entire energy levels are added. So there's a very big increase. This makes it so that an element like sodium, which is all the way on the left side, smaller than krypton, which is all the way on the right, simply because it has one more energy level than sodium. Next, I'm going to talk about ionic radii trends. The ionic radius of an atom is basically how big the ion of an atom is when it has a full outer energy level. Here's lithium, which loses an electron in order to have a full outer shell. So obviously when it loses a shell, its atomic radius becomes much smaller. This means that the ionic radius of all positive ions, cations, are smaller than their original atomic radius. An atom like fluorine needs to gain electrons in order to form a full outer shell. With more electrons in the atom, they repel each other more and make the atom slightly bigger. In the periodic table, we can look at nitrogen, oxygen, and fluorine ions as examples. These ions all have the same number of electrons, but a different number of protons. As mentioned before, the more protons, the stronger the attraction of the nucleus. This means that fluorine, with 9 protons, pulls the electrons closer and has a smaller ionic radius than nitrogen, with only 7 protons. So as a trend, it's actually the same as the atomic radius. The ionic radii get bigger as we move this way in the periodic table, and also get bigger as we move down the periods, because those down here have more energy levels.